So now the last chapter, but only part one. So this is chapter 7, part 1, Living in the World We've Made. So as usual, here are the objectives. We're only going to get through 7.1 through 7.5. Yeah, there was no way I was going to be able to finish that just for next week. So, and as far as the assignment, of course, get that all done. And I'll have this posted. And this is actually based on a parasitologist. It's the only reason I know about Dr. Dixon de Pommier is because, yes, he's a he's one of the leading experts in parasitology. So I know of him, and I have listened to him talk on many subjects. So this is something that he has a strong passion about. You know, you would think it would have something to do with parasitology. Well, he loves that too. But make sure that you listen to this week's lectures, listen to Dr. De Palmier, and answer the questions that have to do with vertical farming and the demand for safe food and sustainable food. By the way, just as a follow-up, now, Dr. De Palmier recorded this in 2010. I just wanted to say that Arrow Farms in Newark, New Jersey is already putting this into practice. So it's not old technology. He's just one of the sparks that started this movement. So post what you think about this, okay? All right. Here are some terms. Again, I think there might be some terms that I add or take away, but this is what we've got so far. So, Objective 7.1, the metabolism of communities. We're going to talk about the urban metabolism in the 19th century. So we're talking about the 1800s. This is before we even knew about microorganisms. Well, we started to learn about microorganisms at this time. So a little bit of history, okay? All right, so here's an illustration of, and actually this reaches way back before the 1900s, but waste management was pretty much, well, you just threw everything out into the street. Now, of course, passersby don't want to be caught out in the middle of this particular event. So yeah, pretty much threw everything out in the street, water, you know, personal waste, dead animals, anything that you had, just threw them out in into the streets, and hopefully rainwater would wash it down into the river. This is something that occurred very frequently in one of the big European cities of Edinburgh, Scotland. And the Scottish population, I guess, had a really nasty habit of not telling people about Gare de Lou. Gare de Lou was what happened every day about 10 o'clock. And before you threw your waste, including feces and urine and all that, out the window, you had to yell Gare de Lou. Row residents would know to get out of there. But they had, again, they had a nasty habit of not telling visitors about it. So visitors might get caught in the middle of Gare de Lou. Gare de Lou is bad French for look out for the water. Anyway, this is what Edinburgh looks like. So you threw everything out the window and everything would roll down the street into the Norloch, which is kind of bad Scottish pronunciation of the North River, the North Loch. And by the way, that was their only source of drinking water. Oh, yay. Some communities live right on the water. Certain areas of Amsterdam and of course, Venice, which we'll talk about a little bit later on, they just threw it directly right into their water source. So that was another way of dealing with it. In London, this is an illustration that talks about the Thames and how all waste products just got dumped right into the main river system. You have dead rodents and dead everything just floating down, and that's just what waste management was all about in the early 19th century and before that. Okay, so let's talk about some maybe alternatives. In the 19th century, there were some privy pits and cesspools. So, a little bit about this. So here we have privy pits, and this is actually in New York City. Let me kind of move back. Sorry. Let me move back to this illustration. Now, you would have some kind of shelter. Maybe you would have a nice little commode somewhere to sit. Maybe not. Maybe you would just squat over the hole, and all the fecal matter would end up in a pit of some sort. Okay? And again, this is New York City. They didn't always have an indoor plumbing, you know. Yes. Now, eventually those privy pits, and also cesspools, as we'll find out, they would fill up. So, because they didn't go anywhere. So you had to hire someone to basically bail it out. You'd have to get somebody in there to just shovel it out. And these were called the night soil men in Great Britain. Also, they did in the United States, there were night soil men there as well. And yes, they would come at night and literally empty out your privy pits, okay? Now, this is not a job people really wanted to do, as you could imagine, but people really wanted their privies emptied. So, you would pay these men actually a lot of money, especially in London. So this was a pretty well-paying job for someone that wasn't born into wealth. Okay. And this is to show you sort of a modern image of night soil men. If you didn't have good sanitation and you had pits, you had to have somebody clean that out. This is just a Game of Thrones reference. If you watch Game of Thrones, there was something just hilarious that showed kind of the process of what you would have to do if you had to clean some of these things out. So this is just an animation GIF. So, yeah, somebody had to have that job. Okay. Now, the cesspools sometimes were not as elaborate as a privy pit. Sometimes there was just a hole and you put a board over it, and that's all you got. But again, it's, yeah, you know, somebody still has to muck it out. They have to get it all the, you know, bucket out the waste product. Eventually, tap water was added, and we had what's called the water closet. If you ever go traveling, they always have signs with a big W and a C on it. That's what a lot of Europeans call the bathroom. Okay, so water closet, which it was. You had a little tiny closet, and in there a commode, and water would have to flush the waste away and away from the dwelling, so you didn't have to have the night soil men, which was kind of nice, but it's going to take some water to do that, actually a pretty large volume of water. This is an advertisement for a very elaborate commode and water closet. Yes, okay. So again, you have to use water to carry away the sewage. That's very nice. That way you don't have to deal with the smell, and it would take it away, far away from the community, hopefully. But again, well, do you have enough water to do that? Safe water. This is just an example of what might happen if you lived in 19th century New York City or Europe. So where are you going to get your water? Where's your sewage going to go? It would be down here. And don't forget these houses, sometimes there would be cesspools or privy pits also there. Now, when it came to drinking water treatment, because remember, a lot of this waste is going into your only source of water. So if you need water, and we're human beings, we need water. So what are you going to do? Because, well, all right, if you try to get a drink of water from the Thames or from the Norloch in Scotland, in Edinburgh, the water's going to be murky or turbid. It's going to be stinky. It's going to have big chunky chunks in there, so that's not going to probably do. Some individuals would drink fermented beverages, and that tends to be a little cleaner. So, but if you did want to drink water, well, normally what people would do is just Worry about the particles. Get rid of the chunks, get rid of the bad smells and the bad taste. And they did start to use charcoal filters in the 19th century. Wasn't a bad idea, but not everybody used those, and it wouldn't filter out everything. Turns out in London, there was a big problem with a water source, and there's a big outbreak of cholera. Now, do you remember Vibrio cholera and how nasty that is? There's a good chance you're not going to survive cholera, right? And you have just those rice stools, and you lose so much water, and you're very, very ill. And it is highly contagious. It's a fecal oral pathogen, Vibrio cholera. Now, there was a huge outbreak in London. Great numbers of people fell ill and died. There was a researcher by the name of John Snow. Yeah, that has nothing to do with Game of Thrones this time. Okay. So he did an epidemiological map where he mapped out all of the cases of cholera. And he realized that, okay, most cases were right around this particular water source or pump, known as the Broad Street Pump. Now, there was a bunch of people over here that didn't get sick. And, well, okay, this was the brewery, so they were drinking fermented beer, and actually fermented products are very, very clean, so they did not get sick. Some people also did not use the Broad Street Pump. There was another water source. Some people used those. But John Snow did a lot of legwork. He was a wonderful epidemiologist, and he figured out that the source was here on the Broad Street Pump. Now, a little back up here. Turns out that because of the high price of getting your privy pits cleaned out, right? The night soil men are very expensive. Well, a lot of people, they just couldn't afford to have them bucketed out. So they would let some overflow. Turns out right next to or close to the pump that was pumping out the contaminated water, there was a dwelling where a young child had cholera. And all of the child's fecal matter was going into the privy, and the privy was old, and a lot of the personal contaminants, the fecal matter, leached out into the water that was being pumped out by the Broad Street Pump. Okay, so that's what was going on there. By the way, this is if you go to London, you can see the Broad Street Pump. John Snow had actually chained this so no one can use it. Now, you might think this was actually where the pump was. Actually, no. They had built a pub around the original Broad Street Pump. This is just for the tourists. But you can at least see the area, and you can go into the pub as well. Okay. So people, to avoid becoming very, very ill, learn to boil their water and maybe do, again, some filtration. That helped quite a lot. But again, there are some things that slipped right through. People didn't really understand germs and the germ theory until, well, a scientist by the name of Louis Pasteur came along, as well as Robert Koch, and both of those scientists were able to prove that there are little invisible creatures called microorganisms, and they can cause disease. That's the germ theory of disease, by the way. So in order to stop the spread and transmission of these microorganisms, Louis Pasteur said, why not boil? Okay, some people are already doing that. And charcoal filters are nice, but he also created what are called porcelain filters. I tried to buy one of these things over eBay once. By the way, yeah, there was no way, because it's so heavy, it couldn't be shipped to the United States without paying a fortune. But a lot of households had these little personal porcelain filtration systems, just like maybe you have a home filtration system. The problem with this, again, is that there are some things that, well, would slip through because they're so small. Viruses, really, really small bacteria, and bacterial toxins would not be stopped by either the charcoal filtration or the porcelain filtration. Boiling might help. Okay, boiling is probably the best, but there might be problems still. I just wanted to show you again that there's sometimes, even in modern times, you can see where waste gets into the only drinking water. So this is, of course, you can see there's a lot of trash in here, and you could just imagine what else is there. And sometimes, and we'll talk about poverty and urban sprawl a little bit later on. I just also wanted to show you Venice. If you ever wanted to see how a society or a city used to function back, centuries ago, visiting Venice is really like turning back the clock. There are a few hints that that you're in the 21st century, but it turns out also that some of their sewer system is the same kind of sewer system that they had, well, back, again, centuries ago. Sometimes personal waste and other things get dumped into the canals, sometimes on purpose, but sometimes accidentally because the infrastructure is so old, the the plumbing leaks and everything just gets into the canal. I have that here because, okay, this is funny. When Venice floods, a lot of stupid Americans like to play in the water. Now I say that this is not me, but I did have fun walking around barefoot in the square when there was flooding. That was rather stupid of me, but okay, I guess I lived, so. Now, let's talk about the 20th century. Well, it wasn't until the 20th century uh, until we started to treat our sewage, okay? So that we had cleaner water to drink, cleaner water for, to treat our sewage as it came down before it got dumped into a river or some other possible municipal water source, okay? Trash, okay, well, trash is quite the problem. In my mom's day, everything got recycled. You reused, well, I should say not necessarily recycled, it was recycled or reused. Everything, tin cans could be melted down. Anything that came in a jar, you reused that. There was very little waste in my mother's generation. But as we got into the 20th century, of course, we have learned to generate an awful lot of waste. And the wealthier you are, the more you can consume things, and a lot of things come in packages. So, and we tend to discard an awful lot. Okay, so let's look at today a little bit. Okay, we're going to talk about waters. We're going to start off talking about water, where it goes, how it's treated, how it comes back. Now, water carries our waste away, and also it's what we consume to survive. And hopefully, you know the fact that the water we have on this planet is the only water that we ever had, and it's the only water we will ever have. So, so in the past, for example, dinosaurs, of course, drank water, and we're pretty much drinking the same water that they drank. Okay, we don't get fresh water somewhere like we get sunlight. Okay, and I say this because I want you to be aware of how precious water is, and what we do with it is very important because we're not getting any more. Okay, so where does it go? Okay, how does it come back? What do we do with it? So to start, let's start this conversation by talking about municipal wastewater and storm runoff. So we're going to start there. Now, when you live in a city, okay, there's a lot of water being used. You know that. There's people in this house, and they're drinking water, and they're flushing toilets, and they're taking showers, and they're watering their yards. And so lots and lots of water is being used. Now, where is it going to go? Okay, well, it goes to where municipal wastewater always goes. There's a treatment plant. So down it goes, and we have plumbing in Western society that takes it to, again, the treatment plant. And cities statistically know what sort of rate the water runs. They're prepared for it. It's on a constant, there's a constant flow. They know how much that is. They're prepared to handle it. And then they treat it, and away it goes. Okay. Now, normally, it doesn't get here to the river unless it's treated, which is a good thing. Now, what happens if you have a big storm? Okay, like a lot of water all at once. Well, this is a big problem, especially for older infrastructures. Certain cities, if it's an older city, they may not have a way to get rid of huge amounts of water very, very quickly. They can't keep up with the amount of water coming down the sewer system. Okay, so this is an episode where, okay, the water treatment plant and the infrastructure is not prepared. So what happens? Sometimes you get backup. Sometimes the water flows and some of it can't make it to the treatment plant. There's just too much of it. So it has to be dumped into the river. Okay, and lots of problems can occur here because, well, it could be carrying a lot of things from the land, fertilizers, pesticides, motor oil, hopefully not, as well as fecal material, all of it getting into the river before being treated. Not good. And, of course, sometimes you get overflow, especially if even the combined sewer overflow doesn't work. So, yeah, all bad. Like I said, this is very common for an older infrastructure. So you have things like New York City and Boston. Those types of areas would really see something like this happen. You would not see this as often in, well, areas that are a little drier and with newer infrastructures. Okay? So what ends up in the sewer? Okay, well, yeah. Oh. So, of course, you have feces, right? Animal waste. But it's not just human, right? Sometimes pet feces can end up down there. Wildlife, okay, if you have a lot of water runoff, squirrel dung, things like that, and animal urine. I know. Did you wonder how I was going to represent that? There wasn't an emoji for urine. Oh, but you know what? This is not the only thing that can end up in the sewer, right? Because, well, okay, we could look at our fecal matter and our urine, and there's probably some bacteria and viruses and, oh, probably some protozoans in there. But are we done? Oh, no. Okay, so let's look at some other things that end up in there. Things that shouldn't be in there. Things that we're not really sometimes prepared to deal with. So here we have a mason jar with nice clean water, but oh, look. Okay, so here's the fecal emoji and some urine in there. And okay, so sometimes diapers end up in the sewer. Yes, they do. They get flushed. And okay, so then we have our herbicides, 2,4-D. Do you remember that one? Uh-huh. Okay, condoms, like the book said. Okay, your dead fish that died on you and you just kind of plunked it in the toilet and flushed it. Or heavens, maybe you didn't like it anymore. Okay. Okay, antibiotics and other pharmaceuticals and pesticides and heavy metals. And, oh heavens, who knows? Sometimes there's things coming from that have been manufactured that we still don't know what it is. So, okay, mystery chemicals, yay! All that can end up in the sewer. So that treatment plant has a big job. Can it handle it all? Well, let's take a look at it. So again, let's take a look at the feces and the urine and break it down. Haha. So when it comes to animal feces and urine, about 90% of that is organic matter. And again, mostly it's just in the feces, not so much in the urine. 12% of what goes in would be nitrogen. That's mostly in the urine. 3% potassium, the 3% potassium would be pretty much in equal amounts, both in feces and urine. 2% phosphorus, mostly in the urine. There's also other trace things that, trace minerals and that, kind of hard to mention there and hard to determine. And, oh gosh, yes, fecal oral pathogens, like I mentioned before, both human as well as animal. And what could those entail? Well, I found this and I thought this was really cool. Somebody went to all this trouble to show how, sometimes this water that you have, okay, and this is actually to show you drinking water, by the way, but it shows you all the different things that could be in the water. But okay, so things that could cause typhoid. Typhoid's caused by Salmonella typhi, if you remember. Things that could cause cholera. Remember Vibrio cholera. Both Salmonella and typhi and Vibrio cholera are bacteria. How about some viruses? Why not? Hepatitis A is a fecal oral contaminant, not a bloodborne pathogen. Noroviruses, okay, those can be in there. Cryptosporidium, the protozoan, can be in there. So lots and lots and lots of things. Yes, indeed. There's a lot to be done just with the normal waste that you would think about. But what about industrial waste? Okay. Well, mystery chemicals, yay! What happens to those? Well, it depends. Some are directly discharged directly into the municipal wastewater system, or sometimes indirectly. Okay, so we've got that to worry about. And if they get into, the wastewater, many times it's not pre-treated. It depends. It depends on what they're making and if the EPA knows about what they're doing. Okay. Now, understand also sometimes it's not just mystery chemicals, but sometimes there are acids in there. And the acids can mess up your infrastructure. They can corrode the metal pipes. If you remember from your chemistry, especially if you had Mr. Seberg, you probably remember that acids will eat away at metals. That's what they do. They corrode metals. So, and this is going to become important when we talk about flint. Okay. There could be, of course, other toxic chemicals, unknowns, right? Okay, so let's talk about sewage waste and taking care of that. So, municipal wastewater treatment. Okay, so when it comes to municipal wastewater treatment, there are 3 objectives of sewer treatment. And really, this also relates to what we learned about when we learned about concentrated animal feeding operations, the CAFOs. What was the problem with having all that animal feces, right? Contaminating water and okay, so this is what a municipal wastewater treatment operation has to take care of. So number 1, remove those pathogens. Number 2, remove all of the organic possible food so that anything that might suck up all the oxygen in your waterways, okay, they won't have anything to eat. So this is what we call this removing reducing the biochemical oxygen demand, or BOD. This is what we want to do. We want to remove organic matter so it's not dumped back into the waterways. Okay. We also want to get rid of suspended stuff, like chunky stuff. That would be good. We don't want to, we don't want to turn on the tap and find a diaper. Yeah, no. No, actually, that's a little over the top, but really when we look at suspended solids, we really are looking at turbidity. You don't want your water to come out like this. You want it to come out like this. So you want to get rid of the turbidity. Normally, turbidity also will probably indicate that there's a potential for other contaminants. Clean water, now it looks like this, but this does not mean it is safe. Let me tell you, this could be loaded with viruses, bacteria, protozoan cysts, and bacterial toxins, and it can still look that good. Okay, just like this, crystal clear, right? But still, okay, this is all hopefully part of the municipal wastewater treatment. So we're going to take care of that. How do we take care of that? Well, here's a pretty facility. This is the Lincoln, Nebraska facility, their wastewater treatment plant. And nice little aerial shot, as you can see. So, okay. So, number one, okay, let's deal with raw and untreated sewage. So, this stuff here, this is what comes into these treatment plants. I can imagine people who work, the public works people, they must just shake their heads. I can just imagine what they see. Okay, so the first thing you got to do is get rid of the big chunky stuff. So there's something called a bar screen. Let me move back here. This is the bar screen. Okay, so as chunky stuff like diapers come towards the bar screen, there's a bit of a conveyor belt. Now there are other ways to do this, but it will remove the big chunky stuff. Okay, all of this ends up in the treatment plant. I know it shouldn't be there, but it can in a lot of systems during certain circumstances. Okay, and okay, this is what can really come up the conveyor belt. Now, there's usually finer screens that will take care of the smaller bits and pieces to remove grit. All of these are going to go to the landfill. All right, so they get carried away. Now, even so, I don't think that's going to be very clean. No, it isn't. So we have these big tanks that are called primary clarifiers. So water gets dumped into this particular facility, all right? And so this is the influent, water coming in, and this is what it looks like in real life from the top, okay? So how does this work exactly? Well, so you pour all kinds of stuff in here, and some stuff is going to go straight down to the bottom. You can have what is called sludge. So the sludge is going to settle to the bottom. Okay, and here you can see there's sludge suction tubes, okay, to carry it away and deal with it later. More about sludge a little bit later on. Here's a sludge discharge pipe, okay. So, okay, and then the scum is skimmed off the top. And what happens is, again, usually there's something to capture the scum, and the fresher water is going to be removed. Here, it's going to leave through a pipe. Okay, so chunky stuff settles and gets carried away. Floaty stuff, yeah, that doesn't sound good, that gets carried away as well. So there's a scum outlet over here. Okay. Now, next two steps include aeration and the secondary clarifier. Okay, so you have to have aeration tanks. As the name implies, you're going to add air. Why? Okay, well, this is where we're going to put bacteria to work for us. Turns out, bacteria can be very hungry, and they can munch up all of this this waste material, munch, and what comes out the other end is much better, much safer, okay? And it's going to have, there's less food particles for pathogens to eat, so this is a good thing. Really what this is doing is it's speeding up decomposition. Bacteria that like oxygen, and some of them do, the aerobic bacteria do, they're going to enjoy having all that oxygen and all of that organic food, and they're just going to go to town. So they're going to have a huge feast. Okay, breaking stuff down. All right, now what do we do with what we get for the aeration tanks? Okay, well, then it has to go to a second clarifier. It's a lot like the first clarifier, although now we have some safer sludge to be carried away. All right, anything that might be floating also carried away, so sludge gets carried away. And we can talk about what happens again to the sludge a little bit later on. For many systems, the water coming out of the secondary clarifier goes to be disinfected. Now, how do you disinfect the water? Well, we tend to use chlorine, which you think of as like chlorine bleach, but it's sodium chloride. Okay. Sometimes there are other additives that might go into the water, but typically we tend to use chlorine. Is that going to work on all the microorganisms? No. Nope, not at all. Viruses don't care about chlorine. Doesn't bother them. There's a lot of microorganisms that won't be killed by chlorine. Okay, so here, this is just to show you, this is what would go into the whole system. So this would be raw sewage, and after the second clarification system, here's the sludge down here that all settled, and here's the effluent that would go off to be cleaned by the chlorine. But again, in here you have bacteria, you have viruses and protozoans. A lot of those are not going to be hurt in the slightest using chlorine. Chlorine won't work on them. Maybe the easier to kill bacteria will. They will die. Okay. Also, the easier to kill bacteria are probably going to be starving. Some bacteria also are not going to be happy with all that oxygen. There are anaerobic bacteria that are pathogens, and they wouldn't make it this far, but a lot would. Okay, so again, some bacteria may starve in this process, but again, viruses don't starve. Protozoans make cysts. The cysts are very protective. That's, once they form the cyst, chlorine won't make the slightest bit of difference. And okay, so we can add the chlorine, but it's only going to be just so clean. This is the whole process. I know this is really busy, so let's just look above the red dotted line here. Here's the water coming in. Some of this could be from, now this could be from your toilet, from your shower, from your yard, maybe. Here's the stormwater base, and everything might join together. Hopefully they would be separated, but sometimes they are not. It depends on the municipal water system that your city has. And okay, from here we have the clarifier, here we have the skimmer. Here we have the primary clarifier. Here we have aeration. Here we have the secondary clarifier. And on to maybe filtration or chlorination. Sometimes it's dechlorinated. Sometimes there's UV disinfection. But understand, any of those chemicals, heavy metals, any of that stuff, okay, there's nothing in the system that is going to take care of all of those. Okay, and they're not even designed to do so, really. Okay. So some processes also have a tertiary step, and there are many different kinds. Depends on what your city bought. So we've got our secondary effluent, and so we could pass this on maybe to a room that looks like this, and we have UV light. UV light, if you use the short wavelength, okay, it's bactericidal, and it would kill bacteria and some viruses. And, it wouldn't do a fantastic job, but it wouldn't be bad. Okay, but like I said, not every city has that. Now, what else has to happen before you return this to the environment? A very important aspect of this is to make sure that you have a load BOD, or biological oxygen demand. When you return that water, the effluent, back into your river or stream or wherever it's going to go, you don't want too much organic material in there. Okay, so yes, organic molecule waste from water, as you go through the aeration process, right, hopefully all of the aerobic bacteria is going to munch through that and not leave any nutrients left. Okay, that's what you want to do. So when you send it back, gosh, it would be nice that the wastewater that you send back has a BOD of 1 to 2 milligrams per liter. Good water quality. Okay, you feed that back into the stream, And bad, what we call anaerobic bacteria, don't have anything to eat, okay? So this is what we want. However, if you add a big bod, like 100 or more, wow, okay, so the water you're sending back from the wastewater treatment plant is still full of organic stuff, okay? Lots of food, stuff that should have been gone from the feces. So this is not good. How does this happen? If you remember from the CAFOs, when you send too many nutrients into the water, the nitrogen and the phosphorus, this is first going to feed the aerobic organisms, but they're going to go crazy. And this is not just aerobic bacteria, but aerobic algae and plants, and they will go so crazy they will use every little bit of oxygen in that river or stream or waterway, whatever. Okay, when all the water is used up, or when all the oxygen is used up, okay, your frogs die, your fish die, your pond dies. The only thing that is left are the bacteria that are anaerobic, because they don't use oxygen anyway. They were in there, probably down in the mud, but with no oxygen, wow, they can take over. And you're going to have very stinky, toxin-making, anaerobic actually, they're cyanobacteria. Remember, this is called eutrophication. This is bad. So high bod is bad. We want low bod. We don't want any kind of organism, food going back into the streams. Same thing as what we talked about with the CAFOs. Okay. So, by the way, as far as the oxygen concentrations after wastewater treatment, there shouldn't be a whole lot of oxygen that we send back either into the streams. Secondary sewage should be removed, or should remove about 85% of the bod measured in the sewage, so shouldn't be a big issue. Okay. What if wastewater wasn't treated properly? What do you think about that? Well, let's talk about that vacation home you'd love to have in Jamaica, right? Here we are, beachfront property. Oh my goodness. Well, yeah, these have got to cost hundreds and hundreds, probably millions of dollars to have such a wonderful property in Jamaica. And look at the water too, by the way. It's so amazing. By the way, this is Grape Beach, or Grape Bay Beach, sorry. And yes, good real estate here, except there's one problem. There is a sewage discharge plant, well, a pipe right here, and there's a sewage discharge zone right next to this beach. And, well, Great Bay Beach is not going to be the only one affected by this. Turns out there was some research done by the University of Quebec and or University Laval in Quebec, and in collaboration with the Bermuda Institute of Ocean Sciences, as well as some other government scientists got together and studied some of this, some of the possible sewage discharge. And what they found was hazardous waste from Hamilton Seabright sewage occurred during rare but some sustained weather patterns. So it did happen. They looked at the water and found that human bacterial counts were 2 times, 3 times, and 4 times what the U.S. sets for standards of contamination levels. Okay, you don't want that. So at its peak, the Seabright outfall dumps between 500,000 to 1 million gallons of untreated municipal sewage from the city of Hamilton, including waste from King Edward VII Memorial Hospital. So medical waste on top of that. I know, I don't mean to ruin your vacations. I'm sorry. But it's just one of those things to think about. Just know that, again, the effluent is less than a half a mile away from a whole bunch of South Shore beaches. Okay, let's talk about some other possibilities for treating the wastewater. Not all treatment plants do this. Some wastewater plants use even more microorganisms to break down what organic material might still be in the sludge and anything that might possibly get out in the effluent. So sometimes they use something called activated sludge. So for activated sludge, you've got air, hungry bacteria, fungi, and protozoa. Here they are. And again, they're going to do a better job and convert the waste even a little bit better. Oxidizing organic biological material, getting rid of nitrogenous waste and phosphorus. And so you just use different organisms to take it a step further, okay, for activated sludge. Now the activated sludge settles out and then taken to a landfill, or it could potentially be burned, okay, and used for energy. Okay, so yes, you can use it for biofuel as well as producing methane. So as these bacteria, some of them are replicating, they will release gas, and yeah, you can collect methane from that. So sludge settles out, solids, you heat up the solids that are left over, and at that point, if you want to get methane, it's the anaerobic bacteria that are methanogenic, meaning methane generating, and yes, they're really good at taking down any little last particle, but also converting that into methane gas that can be burned and used. Okay. Methane used for a lot of things, but methane, if you recall, is it is dangerous. It is a toxicant. So I have this animation just to show what busy little microorganism cells can do. They break down food and release gas. Now these are not methanogenic bacteria that are digesting fecal material and waste from wastewater. Because there's just no animation for that. But this process just shows a fermenter, which is pretty much the same procedure, okay? Just to show you, they're breaking down food and organic material, so, okay, and then releasing gases. And things get changed here. So the food, like the fecal material, all of that becomes very, very different. So, okay. This is just to show you what some of the methane facilities look like. And again, you have to have little microorganisms in there fermenting, and gas can get collected, and that can be used just a little bit later. So this is now called biogas. And the sludge is called biosolids. It's sludge if it's not being used. So if you want to sound cool and green, we call it biosolids. And sometimes instead of saying methane, we say biogas, so as not to alert people that there's methane in there. Okay. Now sometimes these biosolids, again, we'll use that word because we want to maybe use it. It's not just sludge to be thrown into a landfill. Sometimes we can use it as fertilizer because, okay, biosolids can have a lot of nutrients and organic matter. Now, of course, this is not something you want to put into the water. We already talked about that, right? That would give you a high bod. That would be bad. But on land, well, there's some potential there. Okay. And it is very controversial, turning your wastewater into fertilizer and spreading it over your fields. So, well, before this is done, it does need pre-treatment. Okay, got to do that. But still, there's going to be some risks. So, for example, about 50% of the biosolids produced in the U.S. are returned to farmland through a process that is heavily regulated by the Environmental Protection Agency, but it can still have heavy metals and dioxins and flame retardants and endocrine disruptors, all of those things, because that's not taken out in the pre-treatment steps typically. Okay, and the EPA doesn't look at that as much as maybe, well, they're underfunded. I don't blame them. A lot of times they're just underfunded, and that's all there is to it. By the way, pharmaceuticals could be thrown there. Now, if you're thinking this whole process should be taking away, yeah, the pesticides and the herbicides and all of those organic waste materials that we talked about, and the pharmaceuticals, remember all the drugs coming out in the feces. Yeah, no, No. There are a few that might change. I'm not saying they're changed into something good, maybe so, but there are a lot of pharmaceuticals that do end up back in the water. And we do know this. We do know this from studying there are a lot of studies in India that look at the amount of antibiotics being dumped into their water, and some of them, and again, it doesn't go away. This water is the only water you have, and detecting some of these chemicals is sometimes difficult to do and very expensive to take this out. And there might be some, and maybe most of the time it's in low doses. And of course, it's sometimes it's about the dose, but yet dioxins, remember that is in fact, carcinogens or heavy metals. So yeah, and some flame retardants. So there's a problem. Also, the fertilizer, if you remember that during the secondary uh, clarification system, there's still potentially microorganisms in there, viruses and bacteria and protozoans. So you don't want to put this fertilizer on raw vegetables. You don't want to just dust it around and then somebody's trying to eat, a raw vegetable with the stuff on there. This is something, it's just a study that said that maybe some sludge-based fertilizers are causing human illness, and this came out in 2013. And if you want this article, I will send it to you. And okay, and this is just showing you what some of the sludge, when they turn it into pellets, what this can look like. And again, this can be used as fertilizer. From your book, this is Table 7.1. This shows the objectives and effects of municipal wastewater treatment. And, of course, the basic treatment steps, primary and secondary. As far as removing pathogens, most are going to get through the first. Many die off, but a few might still be left in there. When it comes to organic waste, most gets removed in the secondary step. And again, not everybody gets the tertiary treatment, okay? And so it just depends. And removing chemicals always depends on the treatment. Here's Omaha, by the way, because I did show Lincoln, I did not show Omaha. I have this here. This is from their website because I was trying to figure out exactly what they have in place. They've had, MUD had a lot of new construction. There's not a lot of pictures, and I was trying to, this was on their website, this illustration here, and I'm not positive that this is really what the treatment plant goes through, especially the methane, because I haven't heard anything about that. But this is a quote. Basically, their secondary treatment facilities will be replaced with a new activated sludge project and UV disinfection facility. So this is supposedly what we're going to have. But that doesn't really, it talks about the tertiary treatment. So I'm not quite sure about that, but it sounds like we're going to get UV disinfection. It doesn't say anything though about testing for chemicals in the Missouri River. So by the way, this is Lincoln, Nebraska again, and their effluent they have built, well, this is, I think the University of Nebraska at Lincoln built this constructed wetland so that some of the effluent would run through the wetlands. Wetlands are wonderful, natural filtering systems, okay? Not only for, so human wastewater, not just for that, but for other chemicals as well. This is why it is so important to support your wetlands. People who are hunters and fish, and they fish, a lot of times they're great supporters of like making sure that the wetlands are intact, because it's a sport, but there's so many reasons to keep our wetlands happy and keep them out there because they're really great systems. So a lot of the bacteria settle out in, well, fine particulate matter, like in the soil and the gravel, that sort of thing. and there they are rendered harmless. A lot of other microorganisms can break down some of the toxicants that might end up in the water. Not all, but because remember, some are going to be are not biodegradable, and some, in fact, bioaccumulate. So it just depends. But wetlands are wonderful. What about smaller scale systems for sewage treatment? Okay. Some people, if you live out in the country, you probably know what a septic tank is. So, usually you have something called a septic tank and then something called a leach field. That's a leach field for the big facility. All right. So you have to have some tank, and from the house, any waste comes in here. And again, you're going to have the heavier stuff settle out. There's a lot of bacteria that are going to be digesting this. Some of the anaerobic bacteria, by the way, will be releasing gases, so you have to have a way to get rid of that gas. The scum, okay, and some of the water usually drains to the field. And this is actually a better representation. I sort of like this. So here you have what, from the sewer, from the toilet, from the shower, from the sink, and it goes down, and here is a type of a septic tank. And then as it gets filled up, again, some of the lighter material then can head for the leach field. And it has sort of perforated pipes here so that it can trickle down, but this area has to be, it can't be in a wetland or anything like that. You have to have a very dry area so it can trickle down. Okay, so that's really important. So the liquid flows to the leach field, trickles into the soil, pathogens gradually die off. Periodically, okay, you got to have somebody come in and clean out the septic tank. I know. So, like the night soil men. Yeah. Okay, now, when people have septic systems, a lot of times they will try to leach everything to a, maybe a wetland or a leach field. And there are constructed wetlands like I showed you here. And a lot of times, though, if you're talking about a septic tank, you want to make this maybe between the septic tank and the leach field. And sometimes several households together in a community can use this constructed wetland. Some are enclosed. Your textbook talked about an enclosed artificial ecosystem. The book's image was black and white, and I tried to find a more modern image of it. Couldn't do it, so I just used this. So here you have, again, you can have, the effluent from water treatment go in, and you're going to have a lot of soil, a lot of gravel, that sort of thing. And you're going to have to have healthy soil with lots of microorganisms, and they digest the waste and clean the water. And this is a way for some facilities to clean up the water that they use in their toilets. And sometimes the water will come back around and be used in the toilet. Be used in the toilet. So that's awfully green. Very nice. Now, what else can you use? Now, because again, water is so very valuable, using a composting toilet is very, very useful. By the way, I grew up, now my grandfather had a real cabin in Minnesota, and it was an outhouse. And sometimes, you really tend to appreciate the ability to use a lot of water to flush, feces away. But again, you're using really important potable water. So certain composting toilets are very cleverly made so that, okay, to use human feces and human fecal matter for, for a fertilizer, but you have to kind of be careful. And you don't waste water. And if constructed properly, it shouldn't be really, really stinky. So this is, again, a composting toilet, an illustration. It's used in some areas like parks and camps and green buildings. Oops, sorry. And here you have the fecal material dropping down. Usually there's something that will stop any, any gases from coming back up. So you have to have a door in there. And there's a composting chamber here. And eventually you can take out the digested waste. For any liquidy material, you have a leachate that can, again, if you have a field, it can leach out there. The anaerobic bacteria, well, they're going to be fermenting. They're going to be releasing some very stinky, stinky waste. So a lot of it's going to smell like, rotten eggs. So you better have an exhaust system there and vent it away from the person sitting in there. So, all right, I saw this. This was something someone had created, and I think this was a plan for a city in Istanbul. Everything I found was well, it wasn't written in English. So, but I saw this and I thought, what a way to kind of handle some of the wastewater problems and have a park and probably, don't have people romping around down here. But still, they could enjoy all the plant life. And of course, as the plants grow, well, they take in carbon dioxide to get their carbon source to be bigger and bigger. So yes, talk about reducing your carbon footprint as well as working with your wastewater in a very green manner. Okay, very sustainable. But I couldn't find out anything else about it. I just thought, oh, wouldn't that be a good idea? Regulation of municipal wastewater treatment in the United States. Okay, what is that like exactly? Well, we have the Clean Water Act. Yay! This sets the standards for water quality. And there are requirements that say, all right, you have to use the secondary sewage treatment. You can't just do the primary. So no, no, no. Because again, the primary is still going to have an awful lot of organic material and all kinds of pathogens. So no. So it also says, well, this is how much you can discharge back into the water. This is part of also the National Pollutant Discharge Elimination System, And they set standards for effluent, what can get out, and including industrial waste, hopefully. And also they say what kind of technology you can use. So there's certain things that you can use to make sure that what gets back, to make sure that you're treating the waste properly and you're not just sending it back, full of problems. Speaking of problems, now sometimes there's wastewater that doesn't get treated well and something slips by. So this is a little article that has to do with a farm, M&L Farms, and any of their beef, goat, and lamb meat, okay, and products basically had coliform bacteria. Okay, so what are coliform bacteria, you may ask? And a lot of times in the news, you will hear recalls due to coliforms. Coliforms are bacteria. Basically, they are indicators of fecal contamination. So what would be an example of a bacterial coliform? E. coli. Okay, E. coli comes from one source and one source only, and that is the colon. It's named after it, E. coli. Yeah. Okay. So if you find E. coli in water, on a door handle, on a carcass, in your meat, that means that some animal feces got onto that surface. Now, why E. coli? That's not the only fecal organism now, is it? Well, it turns out that E. coli survives pretty much any environment. So if you're taking your time going out and you're testing water or food or something like that, some of the organisms may not make it back to the lab, especially those that are strictly anaerobic. Viruses are too hard to grow. E. coli, on the other hand, can grow with oxygen, without oxygen. They don't care. You really don't have to feed them too much. They're really not fussy, and they'll grow just about on anything. So they are fantastic indicators of fecal contamination, and therefore we make them coliforms, or again, coliforms are indicators of fecal contamination. Okay? All right. So, uh, when we regulate water, it's really, really important to make sure that you don't have fecal contaminants going out of the effluent. Okay. So, like I said, this is what we regulate most, especially in the United States. You can have fecal coliforms. They're not a lot. This is a petri dish. It's a special kind of petri dish that turns a metallic green if E. coli is growing on it. Kind of weird, huh? I know, microbiology is so cool. And also, standards say, like I said, you can't have a high biochemical oxygen demand. So you gotta keep the BOD level low. There's also standards for sludge applied to land. There are standards for metals and pathogens, but again, are they always checked? That, when it comes to, um, regulation, you got to have enough manpower and woman power to get out there and do the tests. So, but there are standards set up. There are no standards, however, for organic compounds. Remember all of those things that are lipid soluble we talked about that, could be used in dry cleaning, and oh gosh, we could also talk about, pesticides and herbicides and things like that. There's really not Clean Water Act regulation for that. Okay. We can have coliforms, but yeah, we really don't have the standards for that. It should be a no-no, and occasionally something comes up. I'm going to change gears. Well, not really. I'm going to talk about something historically interesting. What would you think if I said that a river in Cleveland, Ohio, caught on fire? Now, if you watch the news, maybe you're already ahead of me going, uh-huh. But okay, so in 1868, there was a huge fire on the Cuyahoga River, which means twisted river, by the way. This whole river carried away tons of industrial waste. Okay. And Cleveland, Ohio was a major industrial center. Not the only one. This isn't the only one guilty of this. But here we have a huge fire. The whole river just was set ablaze. And there was risk to life and to property. And this is not even thinking about the poor wildlife and later human health problems with all of this. But, okay, they really didn't have, they lacked sewer and waste disposal regulation in those days, 1868. Just didn't have it. So any industrial waste that you had, well, you'd build by a river, wouldn't you? Because you could transport things up and down the river, assuming the river wasn't on fire. And then if you had any waste, industrial waste, well, you just dumped it in the river and everything would be carried away. Too bad if you're downstream, by the way. So this river in Cleveland was one of the most polluted rivers in the United States. Thank goodness we learned that lesson, right? Well, no. Here it is again in 1952. Oh, here it is in 1969. These are all that I had pictures for, but to be honest, there were 13 episodes of this river catching on fire. Okay. So in June of 1969, that was sort of the last straw finally. 1969, that's what it took. And here, by the way, you can see this is the area when it was on fire, and then they're showing you what it looks like today. I love that picture. It's very cool. So what had happened in 1969, they think floating pieces of oil were ignited by sparks from a passing train. Well, it hit as it was going along the trestle, the metals were making sparks, and there you go, and that's all it took. And there was chunks of wood and everything to feed the fire, so it was pretty bad. The 1969 fire, that didn't cause the most human lives, nor was it even economically the worst economic disaster that they had along that river. but it was the most publicized and the most covered. And by the way, sorry about my grammar. I'll have to fix that. But the good news is that this helped to spur the Clean Water Act of 1972. So, okay, all is well. Okay, well, then we look at places like poor Moscow. This is 2015. I included this because I thought maybe you wanted to see really what, maybe a modern high def picture of a river on a city riverway on fire, what that would look like. So that's horrible. Yeah, but that's Moscow. We kind of know about, Moscow. Yeah, they're not really great in regulation with regulation. But oh, this is Australia. So it turns out that it says the headline is here: people should be terrified. Fracking is spreading. An Australian MP, now this is a member of parliament, so he's like kind of a congressman, something like that. Okay. And he was trying to make a point, and he set fire to the river. So, which I thought was pretty cool. If you want to ever follow that, just click on this particular link that will be on the PowerPoint, so you can watch that. But gosh, the Aussies, they're kind of cool. What's up with that? But in the United States, well, of course, we learned from Cleveland. We'd never let that happen here. Oh, well, here we go. Sometimes the Chesapeake Bay is known to set off a flame or two. I'm not playing the YouTube clip because if I do, YouTube will say that I'm in violation of a copyright law. So if you want to watch this in action and watch her set fire to her faucet, go to this link. She's not the most well-viewed of all the YouTube videos of, as far as setting your drinking water on fire. This one is probably the biggest one, and this ended up on Newsweek, and several other sources reported this. Now, it all started by a gentleman by the name of Steve Lipsky, and he was from Parker County, Texas. And in about 2012, he went on YouTube and started lighting his tap water on fire. So here you can see it. And this is from the Newsweek article, actually. So the reason for that was there's methane in the well. So they looked to add a fracking well, and that was in the area. And the company was called Range Resources. And so Lipsky and his wife sued this gas company for $6.5 million. Now, because of all of the YouTube videos and the public uproar, the U.S. Environmental Protection Agency finally got involved, and they issued an emergency order against Range Resources. But then they dropped the action after the company protested. Range Resources claimed that the methane came from natural seeps far below the bedrock and couldn't be connected to them. So it was a natural occurrence. Okay. Well, methane can come from below the bedrock. That is true. Now, because of this, Lipsky's, they lost their case in court. Now, it turns out that Range Resources launched a defamation lawsuit of $4.2 million. There was a research study group, though. Scientists from Duke University, Ohio State, Dartmouth, and the University of Rochester, as well as Stanford University, got together and did some research and published some papers. And that's actually when Newsweek kind of took over. They said that, in fact, the source of methane in Pennsylvania and Texas was due to cracks in steel casings or flaws in the cement of the fracking wells. Basically, it was groundwater contamination, basically because of inadequate safety measures. Moving on. Drinking water, public systems, and private wells. So what about, okay, public water supplies? So here we are, and there's a happy little household. We have our garden here, and of course we have our bathroom and our kitchen, and we have our washer, dryer, and hot water heater. We got our dog out here, and of course, maybe we're going to wash our car. So, okay. So, we like our clean, potable water, don't we? Turns out the average U.S. family of 4 uses about 400 gallons per day of water. Okay. Approximately 90% on public supplies. That's where it's coming from. About 9% of the population do have private wells, but and about 0.5 to 1% have no piped water at all. And if you're thinking what crazies are like that, well, this is kind of cute. This is a water catchment system from Hawaii. If you live in Hawaii, there's many areas that do not have a lot of fresh water, so you have to be quite clever out there. And a friend of mine lives on an island, and actually she does aquaculture out there. And so, yeah, there's a lot of people that live off the grid because they sort of need to. But sometimes it's because they just want to be off the grid. Okay. Now, when it comes to water supplies, public water supplies, they do deliver healthful water to many people, and they do. And large cities really, they rely on good water. And a lot of the larger cities get their water from surface sources. So, surface water. So, here's the Missouri, surface water. If not the Missouri River, if you're in Omaha, you might get it from the Platte. Okay, or well, from this area, sorry. You might get it from the Platte or maybe Papio. Okay. Now, public systems can also deliver a hazard to large numbers of people. Sometimes things break down, right? So for example, you can, sometimes people drinking water, they open the tap and they get a drink of water and they consume a pathogen, and which can cause waterborne illness. And that is really the major focus of municipal water treatment, because that's really what MUD and the other companies really want to avoid. And of course, the Clean Water Act is saying, okay, you can't have this. Also, sometimes old infrastructures have lead in their pipes. So you might be getting your water, might be getting a little lead with your water, right? Now, why lead anyway? Well, lead was very common, used a lot in the U.S. because you could bend it and make tubes and connect tubes, very malleable. Didn't really corrode very well, so you didn't get leakage, so it seemed like a really good idea. But, unfortunately, lead is a really nasty toxicant, if you remember. Okay, so now things have shifted to copper. Copper is actually really good, and I mentioned that earlier. They will actually inhibit a lot of microbes. And there's a lot of requirements for testing, okay, and you need to respond when you have microorganisms in the water, when you have lead or something like that. So that is what, public systems really are working on. So if you're wondering what this picture is up here, if you remember in Wisconsin, right, they had cryptosporidium in the water, right? All those people got so sick. Yeah, so they trusted their water in Milwaukee, drank some water, and some people died because little protozoan cysts, well, if they get into the water, the cysts are resistant to chlorine, and that was an issue, a big problem. And then when it comes to lead, of course, we have our Flint, Michigan crisis again. So if you remember these pictures, we've come kind of full circle, you guys. So high, yeah. And of course, this was horrible. It really was. And the people of Flint, you have to feel so sorry for them. So one of the things I haven't covered yet was, how did this all come about? All right, I talked a little bit about it, but now let's go into a little bit of detail, and I'll try to keep the story as simple as I can, and I have some pictures that I got, so I'll try to make it as easy as possible. So it all started when in 2014 Flint changed their water source, their supply, and earlier they were using Detroit, a Detroit-based Great Lakes Water Authority water source. Okay, that's what they were using. But they're like, maybe we want our own water source from like Huron. So they said, okay, until we get our own pipes going to Lake Huron, let's just switch to the Flint River and get water there. So they're not going to use what Detroit's water, they're going to use their own river water. So here's the Flint River. Now I know what you're asking. Why aren't they using, why not use Flint's water in the first place? Well, for several reasons, and they used to. I mean, you're living along a river, why not use that for your water? And it was used years ago, but there were some problems. The Flint River had a lot of coliforms, so a lot of fecal contaminants, very, very contaminated, and some other issues too. So, also, they found that the water was very, very corrosive. And, that's not good for old infrastructure pipes. So that's why they, Detroit had to adopt them because economically they were in crisis. And Detroit said, okay, you can have our water source. But then Detroit was going to cut them loose and say, you're on your own. Okay. Now, they're switching back to the Flint water, the river. Okay. So I just wanted to show you here. This is what their pipes might have looked like before they switched. So here we have Detroit water running to Flint. Now, in Detroit, they knew about a lot of their older infrastructure there, and they were adding a phosphate corrosion inhibitor. So that added a nice little film, and that protected the old pipes from anything that might be corrosive. Okay, and some of the things that are very, very corrosive include, well, chlorine actually. Chlorine breaks apart, and the ions are very, very, very corrosive because it's a major disinfectant. All right. So we're switching now, and we're back to the Flint water source. Now, without Detroit's additives, without the phosphate corrosion inhibitor, the chlorine in the Flint River water, okay, the river water was treated with chlorine, sent through the pipes to the households, and there's no protective film here. The chlorine started to break down the metals of the pipes. The metals in the pipes included lead. Okay, that's what happens. Okay, moving along here. Okay, so once, again, the corrosion occurred, some of the lead got into the water and was coming out in the drinking water and in every other kind of water too. So it was in the garden, it was in the shower, it was in the dog dish, it was in, if you had any animals at all, that's what they were pretty much getting. So if you remember, there's a lot of health risks, to lead exposure. And if you remember, the highest risks, of course, are amongst children and pregnant women as well. It has immunotoxicity problems, reproductive toxicity problems, neurological problems. It can cause behavioral problems and increase the risk of cancer. And here's a piece of pipe, and you can see the corrosion here. So all the breakdown of the inhibitor and the corrosion of the lead pipe. All right, moving away from Flint, let's talk about the basic steps for drinking water. This is going to go a little faster than the waste treatment. Okay, so first of all, the water comes in, and before it's going to go to you, okay, before it gets to your household, okay, water comes from the reservoir. This could be, and of course it could be from surface water, what have you. And you're going to get the sludge out, and any sludge, can be carried away to a landfill. Anything that's lighter can be filtered. Okay, and in order to really do a good job of that, you have to have the little particles clumped together. So this is called coagulation and flocculation. So you make little tiny suspended particles bigger, chunkier, and therefore they can get stuck in the filters. Okay, that's a pretty good idea. Well, the reason this happens, by the way, is because, all right, so first, oops. Well, sorry, I thought I had another illustration here. But first you have tiny little microorganisms like bacteria, and they're all negatively charged, so they repel one another. So you add some kind of coagulant, and that would neutralize any negative charges, and now they think they kind of stick together chemically. Okay, like positive and negative charges. And they all clump together with the chemical and with each other. And that's really great. So you get this flocculation. Okay, and clumping. Once that happens, everybody, you can, any big sediments can, again, fall down, and the sludge can be taken away. And so sometimes these systems go in circles. There's further filtration. The lighter particles can be filtered, again, just to make sure that everything gets filtered out. Sometimes they use a sand filter, and that works. And again, when it comes to the sludge that's being taken away, mostly it's water, and mostly it's handled as municipal wastewater, which again, there's several things that we do for that. How about disinfecting our public water? Well, we started to do that to kill pathogens. And the United States uses chlorine or chlorination quite a lot. Well, the reason for that is this. It does tend to kill the most serious pathogens, and chlorine doesn't break down for a while until it hits the air and the sunlight. So as it's being carried through the pipes, there's still a little chlorine in the water, and it will continue its antimicrobial action. But again, unfortunately, chlorine doesn't work on a lot of bacteria. It's not going to work on Cryptosporidium or Giardia. Remember beaver fever, okay? Because those are protozoans. They form cysts. They're too tough. And viruses is not really going to work on them either. So, yeah, so there's going to be some that get left over. So now when it comes to residual disinfection, again, sometimes things, sometimes you get little particulate matter in the pipes like you see here, and you can have rough patches, and sometimes little things can break off. So that's an issue. And plus, the biggest issue is what can happen with chlorine, because chlorine can form byproducts. Okay. So residual chlorine, and here's a truck bringing in the chlorine to treat your water. When it's in the water with other organic particles, it can form byproducts such as trihalomethanes. Now, we call chlorine and iodine halogens. So this is like a halogen and methane, and yeah, it's not good. So this is something that you can be exposed to with a lot of exposure. Okay, and we do know that chronic exposure to trihalomethanes, can cause bladder cancer. How often does this happen? Well, again, it depends on your water source. And some of the research isn't all in yet, but we do know that there is that risk. Okay, we do know that trihalomethanes are formed, and we do know that trihalomethanes in large, exposures do cause bladder cancer. But, as far as how much exposure, what is, remember, dose is very, very important. But then again, you do have prolonged exposure. So there you are. So some public works facilities have actually changed from the chlorine that we normally get to something called chloramine, and that tends not to break down and not to react quite as much as chlorine, and it doesn't make the trihalomethanes. But it sometimes doesn't work as well in the pipes. Okay. Some facilities also use ozone. Now, ozone has a very unusual effect. You have to remember it's a way to form ions, and the ions will break down microorganism cell walls and membranes and things like that. But you can't keep it going through the pipes. So, okay, so ozone is only going to work in the plant, but not as the water's traveling through the municipal water system to your faucet. Okay. I just wanted to show you about ozone again. Ozone doesn't have any toxicants in it, so that is really good. Like I said, you can't maintain it in the water lines. The reason I wanted to bring this up is if you go to the Henry Dorley Zoo Aquarium, you know, what are you going to do if you have sensitive aquarium fish and coral and things like that? They're really, really fussy. Well, you can't use chlorine, you know, and you know, they're living in sort of their own feces. So you have to have some way to clean the water. Guess what they use? They use ozone, and it works very well. This is not from the Henry Dorley Zoo, but if you ever get a tour, they will show you sort of the facility and how that works. It's kind of cool. Sometimes public water has additives put in it, including fluoride. When fluoride is added to drinking water, that is called fluoridation. So why fluoridation in the water? Why add this to your drinking water? Okay, well, the goal is to add about 0.7 to 1.2 milligrams per liter to your water to prevent tooth decay. And yes, studies have shown that this does. It actually protects hard dental tissue, your enamel. Okay, it stops demineralization. You need to keep the minerals there. If not, the bacteria will take hold and produce cavities. Now, the bacteria that I'm talking about includes things like Streptococcus mutans. There's a lot of bacteria like Streptococcus mutans, and they live on your teeth. And when you feed them sugar, what comes out the other end? Acids. And acids will break down the minerals on your teeth. Same thing. Acids and minerals, just like acids and metals, right? Same deal. So you lose your minerals, you lose your protection, and you're going to get cavities, or what are also called dental caries. Well, turns out the fluoride that we use, the hydrogen fluoride, as it breaks down, it gets into the cell, becomes fluoride ions and hydrogen ions, and it inhibits a bacterial enzyme that they need called enolase. Okay, but there are some problems with using too much fluoride in your water and being exposed to it, or let's just say being exposed to too much fluoride. Now, public water is not the only source, by the way, of fluoride. Fluoride is just naturally occurring, and you can pick it up from foods naturally, as well as from water that hasn't been treated. But there is a condition called fluorosis, and this occurs because you did consume too much fluoride over a period of time, and especially when the teeth are just starting to form and appear in the mouth, and you get these little, well, here's a really bad case of fluorosis. Usually this is particularly around the ages of 8 years, well, up until 8 years of age, okay? Now, it turns out that too much fluoride can bother you later on in years. It can cause joint stiffness and pain, can lead to weak bones or fractures in older adults. That's from the American Cancer Society. And bone cancer, probably not an issue. There's so much controversy about fluoride that I was looking at the primary literature and looking to see what people said about it. And I did use the American Cancer Society. And they did say that, yes, cancer, a lot of studies have been done, and they haven't been able to find any connection. So that's one good thing anyway. But the whole deal is this. The fluoride must be applied directly to your teeth for it to work. Okay? It has to be in contact with your teeth in order to work. So, brushing with fluoride toothpaste is a good thing. Consuming fluoride is not going to help your teeth at all and leads to fluorosis. So it all kind of boils down to don't swallow it. Okay, so again, there's plenty of fluoride, so really you don't want to ingest it. It has to be, for the fluoride to inhibit the bacteria that cause cavities, the fluoride has to be directly applied to the teeth. Okay, so really it's not probably a good idea to ingest all that fluoride. But why the big blow up and the big controversy? Well, this all stemmed from a Harvard School of Public Health article published in 2006, but it was sort of preliminary research. And what the research study found was that potentially exposure to higher levels of fluoride in drinking water was linked to a higher risk of osteosarcoma in boys, but not in girls. Researchers linked to the study noted that early results from a second part of the study, okay, so they did more study and it didn't even appear to match the original report. So they even said, hey, have some caution before interpreting the results. But a lot of information was released. People saying, oh, yes, all this water is, it's bad for our kids. And again, the cancer risk doesn't seem to be there. But still, we don't want the high concentrations of fluoride for the other reasons. Okay? All right. By the way, there is one other thing, and the textbook didn't even talk about this, but I wanted to talk about how aluminum concentrations in drinking water and Alzheimer's disease tends to be linked. There was an 8-year follow-up study. Now, aluminum is not the only place, the drinking water is not the only place you can get aluminum, okay? There's other things that contain food that have aluminum, but there is a link to Alzheimer's. And I remember there was even studies before this, but this was in 2000. So just as a little heads up there. Okay. So, household level water supply or treatment. So what about people who have their own private wells and they want to be off the grid? Maybe they have to, maybe it's a choice. Well, the thing is there's no federal standards, but maybe there are state and local standards for drinking water. So here we have, you would want your drinking water, you'd want to have something down deep. You, of course, don't want anything near a septic tank by an effluent of a septic tank, but you want to have a pump that will pump the water up into the house. And again, maybe no federal standards, but hopefully some state and local. Sometimes, though, you do get contaminants, and it just depends on where you live and the geology of where you live. You can have arsenic and radon just as part of your groundwater, unfortunately. And it's vulnerable to contamination by any upgradient land uses. So, for example, if way above on the hillside you have a factory, some industrial processing plant, or even, if you have some CAFO, right? Somebody's raising their hogs or cows up up the hill a little bit. That water could easily then trickle down into your groundwater, and there you go, and you're picking that up. Some people, even though they are getting their water from the municipal water supply, a lot of people, for many reasons, use some device for home water treatment. These are called point-of-use systems. A lot of them are installed at the tap. So you're probably familiar with the pure water system, and this is Culligan. And I don't have any preferences here. Culligan was right there, and they're pretty popular. So I figured you would know this. Colleague of mine, and I think I told you, there's some reverse osmosis systems that people use. And really, if you want to just absolutely be positively safe, that you don't have the nitrates and the lead and all kinds of other things, probably the best thing is to get a tabletop distiller. The problem with this, if you go that route, and they're cute tabletop, relatively inexpensive little apparati. They're kind of a pain. So that's one drawback, but maybe worth it in the end, especially if you don't trust the water that you get, especially if you do have a CAFO upstream from you. But you have to remineralize it. So here's a little trick that my friend Dr. Mosier does. So she saves a lot of the milk containers and other containers. And on the bottom, she has a bunch of gravel that you would put into, you would line your exotic fish tank, because it is, you don't want the stuff that's coated. You want the raw little, looks like little rocks, okay? Nothing glossy about them, nothing coated. For people who keep tropical fish, they know that those fish are extremely sensitive to anything. And the minerals in that are actually really good, and they will leach back into the water. And you need to do that. You can't drink distilled water. That would be bad. It's hypotonic. You'll get sick. So if you ever do use a distiller, that's what you need to do. Okay? And then some people buy bottled water, right? Bottled water. Well, of course, there's the big bottles that you can have shipped. And there's the little bottles. Okay, I have this in here just because I thought it was funny. Diet water. So probably fat-free, low carb. It just kind of cracks me up. But anyway, a lot of people are using bottled water. And unfortunately, the consumption has some problems. It is very expensive, and a lot of sources for these bottlers, these big companies that bottle your water, sometimes they have, sometimes they don't have a lot of water in those areas. They're actually, they actually have a water deficit, yet they're using it to put it into water to ship somewhere else. The people in those areas around that bottler, they don't have very much clean water, so that's one problem. Also, you're going to make plastics, right? And we talked about toxicants in plastics. We also, if you're going to make plastics, of course, you're going to need fossil fuels. And those are going to have to be manufactured in a big plant that's going to burn fossil fuel. And the bottles have to be shipped to the bottler. And then the bottler are going to ship the bottles to you. So, and of course, you got to do something with the bottles when they're done. So very, very, very expensive ecologically. Some of the pluses, though, I guess the water is probably not fluoridated. And it's regulated like food, not like water. So it's FDA. Okay, it's not EPA. So that's rather interesting, and so there has to be a label on it. If you're wondering how they normally treat the water, well, the good news, probably they're not using chlorine. Many times they'll use ozone or ultraviolet light, so you don't have the residual effect. And again, how it's regulated just depends on the state and county. This is just to show you some of the sources of the water. Sometimes it's a well water that comes from the aquifer. Sometimes it's an artesian well, spring water, okay? It just depends. There are many different areas where this water comes from. A lot of times it is municipal water, but it has been treated, like I said, disinfected with ozone, ultraviolet light. Sometimes additives have been in there. So if you go to some of the health food stores, you will find that they are really big about having you buy water that's alkaline. Okay, and I like the Icelandic water just because I like Iceland, but it's kind of a stupid reason to buy bottled water, I have to say. But yes, they say that it's naturally alkaline, and what a great idea that is. And well, is it really all that much of a good idea? Okay, if you remember anything from physiology, your body pretty much has to stay at certain pHs at different parts. So your body has pH buffers, especially in the blood. So if anything does shift, you've got to shift it back. And that's a very good thing. And you have many organ systems that have to also have their own particular pH range. Without that, you'll have enzymes that don't work. So for example, if you don't have an acid stomach, well then, you're not going to be able to break down food very well because you have digestive enzymes that must be in a very acidic environment. So really alkaline, and to be honest, you neutralize some of the good healthy acids. And the acids, remember, in your stomach are a good defense against some fecal oral pathogens because they don't like the acid in your stomach. But then you go drink some alkaline water, not a good idea. Possibly the only people that might want the alkaline water is if somebody is really, really exerting themselves. It could be that, you know, they might be just a little on the acidic side, and it might help a little bit. But really what you should be looking at is the mineral content that's in the water. The minerals really are going to be very helpful in many cases. Okay. Regulation of drinking water in the United States. Okay. For certain pathogens, the Environmental Protection Agency has set maximum contaminant level goals, so MCLGs, and they should be 0. Yeah, please. Okay. And that's a goal, sometimes not very enforceable, but you know, that's what they're looking for. What's a little more realistic is the maximum contaminant level in MCL, and that's a very specific test regimen that they have to, you know, they have to send in the test, and that pretty much puts numbers, you know, again, is still with pathogens. For most pathogens, it's got to be 0. So Cryptosporidium and Giardia and a lot of coliform bacteria. So, you know, at different stages, you've got to test for the coliforms. Make sure there are no coliforms. And again, E. coli is a major fecal contaminant indicator, or coliform. Okay, and again, very important. So the EPA has also said MCLGs, but again, it's more the contaminant level, you know, and so the goal, the actual level, is more readily followed. And they have goals set for turbidity. So here's some beakers, and again, you want to take the turbidity out. And also there are some standards for many chemicals. Many, not all. Okay, the Safe Drinking Water Act also calls for looking out for the watersheds. You know, these are these are probably going to feed where you're getting your water, and they're going to have regular monitoring of public supplies, and public information should be out there on water quality, which you probably already know, right? And like I said, when it comes to bottled water, that's a little different than EPA. We've got the FDA, you know, they're the ones involved because now it's food, and it has to be labeled as food, and got to have all the labels, got to be there, and the quality and manufacturing practices for food should be there as well. How about solid waste and its management? Oh, good. Little more history here. If you lived, like I said, in, okay, maybe Charles Dickens's London. Okay. Well, you might be familiar with the fact that everything was recycled and reused, especially anything that got dumped into the Thames, because again, the Thames, the major river of London, carried everything away. So if you were trying to dispose of a body, maybe a horse, or unfortunately a human being, I guess there was a lot of murders that occurred there, they got dumped in there. Fecal material, again, that got dumped, that didn't get turned into fertilizer. Um, if you had, again, in addition to dead animals, just think of all the things that you throw away, old clothing and rags, and just something that's broken, you'd throw it in there. So personal waste, animal waste, industrial waste, everything got thrown in there. But the waste was a commodity. You had this individual, many times it was a young child, and they called them the mudlark. And they would wade out into the river and pull in anything that was useful. So here are a bunch of mudlarks, and they would be taking all kinds of things. By the way, if there was a body that went down the river, normally they'd look through the pockets to see if there was a watch or money or any kind of jewelry, and then send it on its way. Sometimes they would find clay pipes or, again, rags. Here's someone who was a sewer hunter, and that person's actually straining for anything, maybe change that fell into the sewer line. So there you go. Rags were washed and dried and sorted by size and by color. The white cloth was the most valuable, of course, the size. If you had a nice big white cloth, that could be dyed and used for many different things. So that would be very, very valuable. Bottles could be washed and reused, and, various things got sorted out in the population. So this is how they dealt with huge populations and a lot of refuse. Okay. Here's some more modern pictures if you're thinking, okay, well, here's London, very, very crowded. This isn't really even the slums necessarily. They're tenements, though. Here we have New York City, and you can see there's a lot of waste management that isn't going on. Okay. So when it comes to municipal solid waste, again, it's kind of, you never know what you're going to end up with. Here's something from your book that talks about how, a lot of the solid waste and what what it consists of. There's a lot of products here: paper and paperboard, plastics, metals, wood, glass, rubber, leather, textiles. Again, the mudlarks would probably use all of that. And then we have food and yard clippings, and then other. And if you're looking down here, it's like, oh, polar bears. Well, this may look sad, but at least they're not trying to balance on what's left of an iceberg. So there, it's not quite as pathetic as a lot of the ecology images from Google. Okay. Again, kind of hard to manage. It's one of those things you have to really respect and be grateful for people who do that job. Without it, our lives would be quite miserable. Of course, we have a lot of municipal solid waste, and because we have all kinds of households, the households in the United States have a lot of money, they buy a lot of things, and they have a lot of waste. What happens when you buy a $10 t-shirt? Well, how well is it going to be made? Well, probably not very well. It'll end up being thrown out very quickly, which is a shame. One should maybe spend a little money, get something really good that they know they will be using for years and years and years, that won't peel and rip and won't be too crazy, so it won't go out of style very quickly. But again, sometimes the waste also includes hazardous items. Food waste really should be removed very, very quickly for reasons that I see the animals, and not just, of course, polar bears aren't a problem in Omaha, Nebraska, but we do have, other animals. We do have, for example, raccoons and rats and animals that can carry disease. So, yeah. So, some management options. Produce less waste. Well, that would be really good. So when it comes to percent of municipal solid waste, here we are in the United States. The recycled is this much here. This is incinerated, and this is landfilled. When we're just kind of looking at breaking this down, where are we in the Midwest? Well, we're kind of here. And again, we're not very good at recycling. We don't burn, but we're not the best. So the West tends to be maybe slightly better. Or excuse me, well, yes, the Northeast, sorry. Northeast is probably the best when it comes to recycling, but they also burn a lot. So when it comes to, so what do? You can recycle, incinerate, or landfill. So recycling. Okay, there's a lot of things in recycling. You can compost, especially if we're talking about yard waste. A lot of food gets wasted in this country. But before you do that, you got to get rid of glass and metals and plastic and paper from the waste stream before disposal. Okay. And, certain individuals, certain consumers will use the glass. Some will use the metal. Some will use plastic. My insulation in my attic right now is paper that has been ground up and made and blown into my attic. I know because I was half the team that put it up there. So there you go. And things get sorted and put into recovery facilities. I have this information, or this here. This is why is Nebraska recycling in the dumps? Well, due to low participation rates and lack of an official push, it's as if residents are tossing money into a landfill. And it's a shame. We're not really great here in Omaha. So this is what we prefer to do, unfortunately. And this is what we should be doing. We should be sending all of the recyclables here to be sorted. Composting. Now, you probably have heard about people composting in their back garden, but there is municipal composting. Okay, when you think about all of the agricultural waste, restaurants and everything and yard waste and things like that, there's a lot of things that can be composted. So here we have a huge composter, and this actually allows you to churn the soil, and you want to have lots of good hungry bacteria in there. They'll break things down, and not just bacteria, other microorganisms, and they break stuff down, and what comes out the other end is hopefully the way, if you use the right bacteria, you'll have very nutritious like fertilizer, that sort of thing. There's also you can also do household composting, and if you have room in your backyard, you can do that. Put it in a bin or put it in a pile. You can just add like eggshells and anything else that's compostable. Papers that you don't worry about security, that don't need to be shredded. Maybe put that in there. Also indoors, and I'm sorry, I was going to put a vermicomposting little apparatus there, but indoors you could have, you can put all your compost in there and little worms will break it down, and then you can put it into your potting soil. And this is a nice little confined composter. People like to produce this, especially if they want to do organic gardening. This is confined. Sometimes people will, in their yard, they'll just put up a fence of some sort, or they'll use some boards to contain all of their composting. And there are certain layers that you want to use, and which is rather nice. And you can get this to make good soil, good composting. Okay, now when it comes to recycling, motor oil is actually, it doesn't break down, but you know what? It doesn't really wear out very much either. So it can be reused many, many, many times. This is horrific, looking at this. Pouring motor oil on the ground or into storm drains or tossing it into the trash cans, even if it's sealed, is actually illegal. You can't do that. But why would you do that anyway? It pollutes the soil and the rivers and the stream, and it's very, very dangerous. So you wouldn't do that. So why do we bring our things here? So why do we bring our filters, our oil filters, and our used oil to places like this, facilities like this? Well, okay, the used oil can be sent to petroleum refineries to produce gasoline. I know it's going to add, I know it's going to add greenhouse gases and all of that and pollutants, but all right, well, but this is one, instead of buying fresh oil, okay, it's still greener than buying it, buying it in the can, without having it, without buying recycled oil, okay? You can filter it, remove your contaminants, really get rid of any water that might be in there, and use it, burn it to power industrial operations or just to make heat. But again, okay, sometimes it's not a very green option. If you really want a very pure, almost virgin oil product, okay, you can do that. It can be distilled, dewatered, and what's called hydrotreated, and that'll get rid of all contaminants. And again, it's almost exactly like what you would get if you just got it right directly from the refinery. So, good stuff. What about incineration? Let's just get rid of the problem. Set it on fire. This is actually from Arizona. Well, and then what you have left is just pretty much ash, so you reduce the amount, the volume, the hard waste, and get rid of it. But, okay, you are releasing, okay, a lot of gases into the atmosphere. Probably a lot of them are going to be greenhouse gases, so not good. Sometimes the waste that we get, if you set waste on fire, some of that waste can have a lot of really nasty toxicants. I know somebody who wanted to put packing peanuts as insulation in his house. Mind you, if that ever caught on fire, the fumes from that would be horrendous. So there's a lot of things in waste that you do not want released as particulate matter and released as gas. Okay, that would not be good. So again, the challenge is there's metals, heavy metals that that could be in this. You could get mercury vapors if you tried to incinerate it. Any emissions must be captured. The smaller particulate matter is what was called fly ash. That's the worst part. Any plastics are going to have dioxins. Remember those. Okay, carcinogens, really seriously nasty, and furans. And again, you're going to get those if you don't get the temperature high enough. So a lot of problems can occur with incineration. What about landfills? Well, that's pretty much what we do here in Omaha. Most landfills have to be licensed. You can't really have open pits anymore. That's pretty much illegal in the United States. And usually they're owned by corporations. So in order to do this properly, you better have the pit lined. Sometimes with clay, sometimes with plastics, because you don't want any liquidy stuff leaching into, say, a water source. But again, that's a problem if you have a water table that comes up, okay? So that's going to be a problem. So it's lined. The trash comes in layers. So you have, again, the dump truck dumping all the trash in there. And you got to cap the whole thing with clay. And sometimes, again, if you have water coming down, there's a leachant, so you want to get rid of that. And here's a leachant pump. And it's going to have to be, put into a storage tank for safe disposal. Sometimes you have anaerobic bacteria in here, and guess what? The methanogenic, the ones that generate methane, can be in here. So a lot of times you're going to have methane gas coming up. Okay, actually that happens a lot. Hopefully not any leaks. The methane, again, can be sent to to be used as fuel to generate electricity. And but the thing is, again, if the liner leaks, if the pipes leak, you could get any of the landfill leachant getting into water sources, methane gas escaping into the atmosphere. Not good. What about medical waste? These are waste produced by healthcare facilities. Well, okay, hopefully you know there's very specific things that you need to do with medical waste. Usually there are biohazard bags that medical waste has to be put into. And you have sharps containers, all of that important stuff. And there's special treatment if you're working with radioactive isotopes. So it's infectious, hazardous, and radioactive. So a lot of times for healthcare facilities, medical waste do need to be incinerated, but there are federal standards to make sure that emissions are limited, and but still the majority has to be regulated also by state and local governments. This is New York City, and this is medical waste being dumped into the river. Don't you love it? So the old-fashioned way. Yeah, we don't want to go back. I just wanted to talk about, yeah, sanitary landfilling, the way that we know. We used to have open pits, and of course that's really not a good way to get rid of all the refuse that we, as a waste-producing nation, you know, as for what the way we like to consume. So we need to really, we needed to go to the more advanced landfill facility. But we've been doing sanitary landfilling since probably the 1960s and early 70s. So there are benefits. Again, you can reclaim land eventually, and that's important as populations are increasing. It's economical. You can turn the land into a golf course or football pitches. Our farmlands, the parks and farmlands do have a problem with that, and we'll go into that in just a little bit. The problems, though, again, is that sometimes there's a leachate that is toxic, and it can affect plants and fish. Okay, so that can be a problem. Also, again, like I said, the methane gas can leak. And landfill gas is being produced for 75 years or more. And so that's going to be there for a long time. And it's going to be very detrimental to the plants. Methane is very toxic. Very toxic. Okay. And remember, methane is a much stronger greenhouse gas than carbon dioxide ever could be. But sometimes carbon dioxide gas can be leached up or can also be released with the methane gas. So yeah, that's not good. You know, sometimes you get oxygen as well as ethylene. Also, when you have land like this, you have to be careful. You really can't plant trees, and you can't build big facilities on this, and here's why. Tree roots could penetrate the cap. So if up here you have a clay capping, you cannot plant a big old tree. Also, if any toxicants, if they're coming up, if they are water soluble, they will get into the plant material. So this farmland idea, I don't think is really a good idea between you and me. Parks, okay. But again, you really can't have the trees. Or if you do, they have to be very, almost shrub-like. Okay. And again, the Resource Conservation and Recovery Act says no open dumping. You can't be doing this. You got to cover it up, and that's, you know, and there are many requirements just to make sure that you don't have groundwater leaching. You want to monitor that. And what most municipal systems, you know, well, most communities, they really stress, let's reduce the amount of waste that we have. If we recycle, okay, maybe convert some waste to energy, that would certainly be, you know, maybe that's a little better too. Recycling always the better idea, because incinerator emissions, that's a problem too. Okay, this is just to go into the methane inhalation. So inhalation of toxic gases of methane can cause pneumonitis, and yeah, methane gas is quite the intoxicant. So it can cause loss of consciousness and asphyxiation, and at some point it can cause constriction of the breathing, the airways, and you know, so just not a good idea. You have to kind of be careful around those. Also, if you do have a landfill, you have to be careful of erosion. Hopefully it's capped really well, but here we have some cattle, and this is an old landfill. Yeah. So there's always, whenever you have a landfill, it is always going to have some effect on animals and plants. So, and some of the material in the landfills we know leads to mortality, from mortality to decreased fertility on those animals, as well as plants. And certainly if it gets to you, well, what could happen there? Let's talk about handling of household hazardous waste. Of course, there are a lot of things that you need to dispose of properly. A lot of communities will set up sites where you can bring your old chemicals, because a lot of chemicals have some really nasty, corrosive, toxic, ignitable, and reactive chemicals. So if you strip furniture, I was just talking to some friends this weekend, um, about stripping furniture. That's pretty nasty. Drain cleaners, rat poisons, antifreeze, pesticides. Okay, like this old chlordane ortho pesticide here. Yikes. And again, you know, it really requires special handling. Um, Again, most cities and towns do have some programs for disposal. Let's talk about urban settings in less developed countries. So, yikes. All right. Just when you're starting to feel kind of grumpy about, you know, the FDA and EPA and all of that, and lack of government regulations. Okay, well, still, we can sing the national anthem a little bit, because you know what? There are a lot of people who just don't get potable water and barely get water at all. And sometimes there's some real risk just to get the water, and then risk when drinking the water. So, yeah, there are some really, again, something to consider. Especially as a lot of the global population is becoming urban. We used to be more rural, you know, farmland, that sort of thing. But people move to the cities, well, for good reason. That's where the jobs are. Hopefully that's where the opportunities should be, okay? About 3 billion people live in cities, amongst them 1 billion in urban slums. Here you see, again, there's a bunch of what's called megacities, and I have a chart from your textbook, or a figure. There's an estimate that there'll be about 37 megacities by 2025, and this is from India. So as you can imagine, although this doesn't look as horrible, because at least there's a couple trees, but I wonder how the trees aren't looking all that healthy. This is just looking at some of the mega cities, and Tokyo is, of course, the largest. Or maybe you didn't know that. Delhi, Newark, right underneath that, Mexico City, Shanghai, Mumbai, Beijing, um, Buenos Aires, Manila, Paris is in there, and yeah, so it's there. There's some problems, and I mean, that's going to be hard to deal with, all those people crowded together. And of course, when you have so many people, there's always going to be the impoverished, excuse me. So yes, poverty, crowding, poor housing, lack of sanitation, lack of clean water. These areas, usually they're going to be exposed to the most air pollution, toxic waste, fires, traffic accidents, violence. And as you can imagine, okay, where's the waste going to go? You don't have a lot of places for waste disposal. So people are crowded, okay? They're probably going to be pretty sick, and there's going to be a lot of infectious diseases. And where's your medical care? So community medical care is vital, yet they're not going to probably get it because they just don't have the economic wherewithal. Standing water, that's going to also breed vectors of disease, your mosquitoes and things like that. But again, lack of sanitation, big problem. This is from your textbook, and this just shows Ecuador, an Ecuadorian city, and they're all above the contaminated water. So you can imagine how the sewage is moving. And yes, I've been to Ecuador, but I have not seen. Luckily, I did not see anything like this. Maybe I should have, huh? Okay, so this is the end of Chapter 7, Part 1. And don't forget to to watch the video and do your project for the week. And let me know if you have any questions. And we will only have one more lecture, and we're done. Yay! Take care.